Obviously, some of it's moving with or opposite the direction of the wave, and some of it moving transverse to the wave. So a number of textbooks don't include this because this is just a combination of these two. Some do. I include this just in case you happen to run across it.
So what is it called?
A surface wave. But it is also a mechanical wave because it does require particles. There has to be something moving, particles moving. And then, as opposed to mechanical waves, there is something that doesn't require particles to move. So, in things that can be transmitted through space, which is fortunate that they exist because otherwise we would never see any light from the sun. Known as electromagnetic waves. It's actually not hyphenated, it's one word. Electromagnetic waves. Usually shortened to EM waves, or often shortened. Now, electromagnetic waves is not part of the chapters we're doing right now. They are other waves that can travel through the vacuum of space. Radio waves, television waves. They still do television waves. Microwaves are all examples of electromagnetic. Visible light also part of that. All right, any questions about our initial round of vocabulary? So now, when describing waves, we have a couple other vocabulary words specific to waves, and one of them is amplitude. See if I can actually write neatly or not. And amplitude is just how big the wave is. More mathematically, if I figured out what the middle is, sort of whatever the middle of my high and low pressure are, for example, amplitude would be from the middle to the peak or middle to the trough. The units of amplitude really depend upon what you're talking about. If it's sound, then the amplitude could be in terms of decibels or bells, or it could be in terms of pressure. This is an example of an amplitude of a wave, and this is an example of a smaller amplitude of a wave.
I was wondering why you got loud. I was gonna say, what are you yelling at?
Just doing physics. All right. The symbol usually is case specific. If I'm generically writing amplitude, I'll just use a capital A, but I'm not going to write anything specifically down for that like I will for the others. So frequency, another common word. The symbol for frequency is an F. I basically use the same F as I use for friction. And frequency, in essence, like the word frequency, it's how often something occurs. So it's basically the number of cycles per time. Think of a cycle. Think of any repetitive motion. A cycle is just one of whatever is getting repeated. So if I'm going up and down with, go back to the battle rope, if I have some long coil and I'm going up and down with it, then the frequency is how often does my hand go up and down and get back to where I started. We do have units, SI units for frequency. It's cycles per time, so the time is usually in seconds. So cycles per second, which is just a hertz. Named after hertz. Period. We've dealt with period before. There it is again. We dealt with period before when we dealt with orbiting, about how long it takes for a planet to go around the sun. So the period of the Earth going around the sun is 1 year. Just more generally, it's the time it takes to do one cycle of repetitive motion. Trying to do one cycle of repetitive motion. So frequency is cycles per time, period is time per cycle. It's just the reciprocal, it's just the flip of each other. So the SI unit, seconds, it is time. Or seconds per cycle, also works. But as just talked about, frequency and period are reciprocals of each other. So for example, if I have a sound that's playing at 2 hertz, not that I would hear it. So it's a frequency of 2 hertz. How long does it take to create one cycle of it? Well, this is basically saying it takes I create 2 cycles each second. So the period would be flip of that, 1/2 seconds per cycle. If I can create 2 cycles in 1 second, it only takes a 1/2 second to do 1 cycle. And there are probably enough students gone that we can go out into the hallway now. Just that. Yeah, we'll take this one. All right, let's head out into the hallway. Let's actually film this. I've done this before where we've done the filming of the board while I'm out in the hallway. And if you have good headphones, you can hear what I'm saying. However, all right. Do I have a volunteer? Thank you. If you would be seated over there.
Seated?
Yes. Does that change your mind?
No.
All right. So for right now, I just need you to hold that in of the coil.
The coil of or the?
Whichever one's more comfortable for you.
Okay.
All right, so basically I'm going to send a wave down to that end.
Oh.
Now, what I want you to observe is what happens when the wave gets to her hand. So what happens when the wave got to her hand?
It went back.
All right. How did it come back?
It bounced off.
Okay, so that's known as deflection. Like, Latoya?
It did like a little squiggle or whatever. Right. It went back. It went it went back and then it came back. But
Okay. So when I sent the wave down, I'm sending it down on this side. When the wave reflects, which way does it? So with Latoya holding that there, that's known as a fixed end. So when the wave gets to the fixed end, it will reflect on the opposite side. Now, let's look at a free end. If you would take the metal bar and sort of feed it through one of the loops down there.
One of these loops?
Believe that. I want your end to be able to move freely, not that direction.
Oh. Oh, like this?
Yep, there you go.
Okay.
Sort of put that in the middle. Put your hands as far apart on the bar as you can. All right. So now I'm going to send the wave down. I'm going to now send it on the other side.
Oh, wow.
Which way did the reflected wave come back?
The same way.
Sorry?
The same way that you sent it.
And that's what it's supposed to do. A little harder to see, I think, but.
Okay, I see what she's talking about.
So I send it on this side, it's going to come back on the same side. So that is a free end. Now, in terms of something a little less tangible, if I've got a tube with water in it, and have you done the speed of sound lab?
No.
No, okay. The bottom where the water is the fixed end. The open end is a free end. So in terms of sound. All right, finish with the rod. We'll come back just to this. All right, so she's going to have a fixed end down there. I'm going to send the wave down, and it reflects back on the other side. So now, I want us both to send a wave at the same time. So I'm going to go 3, 2, 1, go. And when I say go, let's both come out to here and back.
Okay.
3, 2, 1, go. Now we both sent waves towards each other. What happened when they met?
Kind of bounced in the middle and then just came back to how we started it.
So they bounced off each other? Is that what you're saying?
Yeah, and just kind of looped right in the middle and then just came back.
What would happen if they were on opposite sides?
They would probably just collide together.
And?
Mister, there would be a collision.
Well, let's find out what happens. All right, so this time, yeah.
I don't know the word. I forgot the word that it would kind of turn into if the ripple turned and came into like close contact with each other like that.
All right. Let's just do the demonstration and then we'll sort of parse it. So I'm going to go to here and you're going to go to that side.
Okay.
3, 2, 1, go. So what happened when they met?
They just stopped. They just stopped.
So nothing went past it once they stopped?
I don't know, did
Can
they?
you do it again? Because that was a little funky in my eyes.
All right, 3, 2, 1, go.
It seems like it sends it back,
Yeah.
but like in the opposite direction. Wait, no, it doesn't. It doesn't go that way.
So you're saying they bounced off each other but flipped sides? I thought that's what you said.
I did, but then I forgot. So.
All right, let's take a look one more time. 3, 2, 1, go.
Yeah, they bounce back in the opposite direction.
Anyone with an alternate explanation?
It just looks like they hit each other and then they just go straight, like back to where it was. I don't know.
So you're going with they bounced off each other.
I'm thinking they bounced off each other and then just came straight.
All right, so let's try a little bit different look here. We're going to go to the same side. I want you to go about where you went before, and I'm going to go farther.
Okay.
So they'll be unequal in size, in amplitude. Okay, 3, 2, 1, go.
Whoa. We did what? Dude, can you do it again?
All right, 3, 2, 1, go.
Oh, they just both went the same way. You both just went the same way.
But as in,
Like, you swung the thing that way.
But I think when it went that further, it kind of brought it more to that way and then quicker back this way.
It should have been more to that.
Yeah, it went further that way, cause you went that way, so it kinda pulled it that way, but then it kinda went right back. Like a
Does it not bounce back? Do they just pass each other?
They just pass each other.
How does that, what do you mean it just passes each other?
Because when they're meeting, they basically do something, and that's the next question is what happens when they actually are together, but they just go through. It's not that they bounce off each other and come back like that, it's that they pass through each other.
And that's what okay.
And so when I said the larger waves, I think there was more of a bounce at your end afterwards than at
Yeah,
my
I
end,
felt
because
it.
there wasn't the reflection, it was passing through. Reflection doesn't get there until the end.
Okay.
Alright, so let's look at, with that lens of they pass through each other, let's take a look again. We'll both go out to about here. So 3, 2, 1, go. And then opposite sides, 3, 2, 1, go. So, yeah, there's a bunch of wiggling there. Let's see if I can see a little bit more slack. It should go a little bit slower. Same side over here. 3, 2, 1, go. And then opposites. 3,
Sorry.
3, 2, 1, go.
So I can see what you, I can see what you're saying, kind of like rolling and then just going like, I can't explain it, but I can see that kind of roll through and not really stop it, but your end is still making its way through this way, and my way is still making its way towards you.
All right, in that last case though, what happened when the waves overlapped?
It seemed to make another ripple, almost.
Okay,
It looked like yours went down here. When you guys went opposite ways, it looked like yours was like went farther out and came this way. And then hers just like blended in with it.
and as in hers just disappeared completely?
That's what it looked like. I don't know if it's because you're doing it harder or
All right, just hold your end still this time. Okay, so that's what it looks like with just me. All right, so now opposite sides. 3, 2, 1, go.
or maybe hers is just delayed. I don't know. But
And
it looks like yours is coming all the way here, and then hers is just like,
hers doesn't quite make it to me.
huh?
It does make it to you, but it just seems like mine's is kind of like like you get yours down, even though we did it at the same
Well,
time,
can you
it's
do it
like
again so
yours
I can
come
watch
down
your
and
side?
then
All right,
mine.
so
It almost
3.
seems delayed.
Yeah, that's what I was
Yeah,
thinking.
that's what I was thinking.
If hers is delayed, if I'm doing it before she's doing it, that just means they meet at a different spot. But we'll try it. All right, 3, 2, 1,
Which way?
go.
Oh, was that supposed
I'm
to
going
be-
farther than you're going that time at least.
Okay,
So opposite sides.
okay.
So 3, 2, 1, go.
It just passes. I mean, hers still gets to your side. I don't know. They kind of all look the same at this point. We've been
All
watching
right.
this thing for like, this
Let's
one
pay
time.
attention to the thread there. Is that it's not really in the middle. There's the piece of string, red string that's
Okay.
tied there. Let's first go to the same. So I'm basically going to bring my end to about here, and she's going to bring roughly the same distance. So we'll go to the same side. The question is, how far does that thing move? So
So
3,
keep pulling it.
3, 2, 1, go.
It went to where you pulled it to.
It just went to the side a little bit and then came back.
I'm trying to put that in the middle. Is that how far close do I need to get for that to be in the middle?
That's not even close to anything.
Yeah,
Maybe a little more. So it's-
Honestly, just get, yeah.
That'd be fine.
Okay, you've got a better view than I do. All right, same side. So we're basically bringing it out a foot. 3, 2, 1, go. So I brought mine to here. So if it went out as far as we moved our hands, it would come out that far.
It looked like it did.
All right, sorry. Let's go back in 3, 2, 1, go.
Oh,
Did it
it's
go
next.
further?
Oh,
Hey, a little bit bit further. When the two waves meet, in a nice ideal situation, and this reason we're doing this here instead of the carpet is this is closer to it, but still, the wave's not going on forever.
You're talking about the ripples that it makes when it goes this way.
Say it again?
Maybe the ripples that keep going further out as we like drop something. Go ahead, sorry.
Yeah, and so eventually the ripples disappear. But in a nice ideal board situation, you put a drop in a bucket of water, that ripple would go out, hit the sides, come back in, so they keep bouncing on forever.
So what we was looking for, just how far it went with both of us,
Right.
hitting it and then coming back.
So when the two waves met, they added to each other. So ideally, if I moved it a foot, she moved it a foot, when the waves met, it should be 2 feet. Now, we're losing energy as we go. It's not going to go as far. Friction is a reality. But when the two waves meet to create something bigger, that's known as constructive interference. Now let's go to opposite sides. Someone straight there. All right. 3, 2, 1, go. All right, one more time. 3, 2, 1, go.
It's not really going anywhere. We just got, just looking at that, it just affects like a little bit.
So when the two waves meet, they cancel each other out.
Slows it down.
It's known as destructive interference. So at this point, if I send a wave down, we've shown before that if that end is fixed, the wave's going to come back on the other side. If I send a second wave, it's going to interfere with the reflection of the first wave. And so I can create these patterns in the coil here. So back so I've got some room. All right, just keep your end fixed. So I'm going to send a wave down, then I'm going to send a second wave. So first wave, second wave. You almost could see a pattern there, so let me just keep it up. All I'm doing is just doing the same thing I did before. I'm sending a wave down, the reflection is coming back and interfering with the next wave that's getting sent. Notice that there seems to be a pattern here. You got these points which move a great deal and these points which aren't moving much at all.